Very happy to be here to finalize my last talk as my PhD student. So it's my dissertation, more like an overview of my dissertations of, about building up a robot cerebellum towards safe, agile, and intelligent like robots. So let me introduce like robots. Why do we need like robots anyway, right? Because, human environments are mainly designed for legs. So having like robots can better coexist with our human beings. This is our long shot dream. And secondly, I think recently it's more like I think this is more like another increased in tendency that if we really want to use data, and there are so many data about human online, for example, and it's the easiest thing we can get data from. And but if you want to use the whole body motion data, and then of human, and then having a biped, a humanoid robot, which has the most resembled morphology as humans will be the best embodiment. So yeah, so my research goal is to actually create the next generation of dynamic robots of the AI era. So spanning from 3 axes, so agility and safety and intelligence. I'm interested in how to enable this robot to perform agile and robust maneuvers in the real world, and how to enable this robot to safely and autonomously navigate in unknown environments, and then how to push this robot to go beyond just like locomotion and do something more interesting and useful tasks, such as manipulations. So, in one sentence, to summarize my current research is that I'm building up the robot Cerebellum. And in the future, I want to keep pushing the boundary of these 3 axes and to build up the entire robot brains by actually incorporating more sensor data and more perceptions from the real world, to perform more advanced athletic intelligence by interacting with the environments, and by how to change the environments and how to avoid safety disasters, like when this robot is operating around human beings. So, but this it's very hard. Problems like locomotion is very hard. It's actually known as a Merrill-Box paradox. That is, it's quite easy to make the computers win the chess game, but it's very hard to make this computer to have a same level of mobility, even compare with 1-year-old child. So why is this problem hard? Let's give a Cassie as examples. So Cassie is a biped robot. For example, it's our main test bed. You have 2 legs. Each leg have 5 actuating motors denoted by the red arrows, and 2 passive joints denoted by the blue arrows, which are connected by the leaf springs. Contains floating base have 20 degrees of freedom in total. If it's nonlinear system, when it start to work, it becomes a hybrid system. It's under-actuated because of its floating base. The robot need to make contact with the environment in order to move. So we can actually use Lagrangian to write down its dynamics functions, and this is like what we obtain. This is actually a general form of F equal to ma. Okay, but it looks quite simple, right? Just like one line of equations. Actually, we just write, if we write down all the details of these equations, we actually obtain a huge file. And this is only a small part of it. I'm just screenshot these kind of equations. In fact, we need 3.6 megabyte of C code just to store this kind of file. So such a high dimensionality and high nonlinearity makes tackling the problems on this kind of robot very challenging. So what did people do previously, to tackle this? Usually people formulate optimization problems. It's more like structured optimizations. So we start with some cost functions, and we have some constraints. And the constraints basically, the dynamics constraint was definitely one of it. So we need to rule out our dynamics models over horizons. And we need also enforce some contact constraints. So since, the trajectory breaks at this contact, so planning the contact mode online is quite computationally challenging. So most people do is to pre-specify contact plan. For walking, for running, for jumping, they are just all pre-specified contact plan. When to contact, they are all pre-programmed. So this actually makes this kind of method not that scalable to different locomotion skills. And also we have other kind of constraints. Okay, but I think the true computing complexity coming from this kind of a T, we need to not only need to emphasize or in constraint the enforced constraint at every time, the current time step, but also need to rule out our dynamics over horizons. So such a kind of, so such a rule out online to do the prediction controls is quite complexities. They're quite complex to solve like online. But, so then people had to start to, think about whether we can simplify dynamics, all the stuff, and have do some work on, make this kind of sort of happen online. And then there is a lot of kind of different models people develop to tackle these problems. And then we had to have a spectrum of this kind of a model-based method. So I think the state of art, I think, is still Boston Dynamics. They develop a hierarchical model-based controllers, namely MPC, and then they can make Atlas to do very cool agile maneuvers in the real world, such as parkour, dancing, all the stuff. But I think the challenge of this method is actually that we really need a good model, because we cannot model all the details of this on the hardware, and even when we're able to do so, it will be too complex to use to solve. And we all know that behind the scene of these all cool demo videos from Boston Dynamics, there are lots of tuning efforts happening, and there are lots of failure case behind the scenes. So, but they have a company and they can repair the robot very soon, right? Overnight. But what if our model is not good? This is actually one recent example from our lab. We are actually building our own humanoid robot, which is named as Berkeley Humanoid from Chayuan's. And he actually developed a very nice model-based controllers in simulation, tested very nice, perfect fine in simulations. And once it's deployed on hardware, the model went wrong and the controller just blew up, and it just blew up entire leg on hardware. It is really true. This is actually blown up by an MPC controller on hardware. Yes, and then the students kind of get frustrated and they need to go back and repair the robot and then develop algorithm again and to keep fine-tuning the parameters probably, and then redo the experiments again. So then this kind of back and forth, break the robot, repair the robot and do it again, tuning the parameters on hardware, kind of tedious and time consuming. It's actually one of the reasons why in the past decades, black robots community is kind of moving that slow. It's because of this kind of huge amount of engineering effort required for hardware, and only limited labs and companies are able to do so. And then tell the student, why don't we try the reinforcement learning method? And then the student just go back and train our policies in simulations in 2 days, and then deploy the policy on hardware, and then works perfectly fine. So what actually happened to make this kind of, developing like locomotion control that easy and that, streamlined it? So what has changed? So let's go back to this timeline, and actually around 2020 and 2021, we are actually one of the first, along other notable work in the community, to actually introduce reinforcement learning like locomotion control in the real world. At that time, our work showed that it's not the iron is not only able to control the robot in the real world, but also make it very robust. It actually show a very significant robustness over other methods, especially over the traditional MPC methods. At that time was a very surprise to the community, because at that time people only believe reinforcement learning can just control the simulated characters in the simulations with some funding gates. So then lots of people coming in because they find this very interesting. They find this method may be helpful to their own research and their own robot. So then we witness explosive development of a reinforcement learning based controls in like robots. So different people come in and develop their own algorithms, recommend their own design choice, and show their very cool demos. And as you say, this kind of a field have been, has progressed in a very significant amount of, have been progressed very significantly. Okay, so last year, so we actually write our own journal paper to summarize all the design choice we recommend and all some lessons we learned during the development of our own IO-based controllers, and show all different generalized different locomotion control skills in the real world hardware, real world biped robots. And then I think that now the community start to progress towards another stage, which is to tackle more challenging robots, which is biped humanoid robots. So I think in the past 5 years, I have become another paradigms alongside the model-based controller in the electrical motion. So let me walk through this journey to introduce our effort to make this happen. So what do we solve? How do we solve these problems? We first studied the model-based optimum controllers. We can all-round optimization offline, and we can also come up with some reduced order model to simplify the dynamics and do the optimization online. So good things is that, as I mentioned, the models give us our structures, so we can actually explain everything, and we can model everything and we can explain it, and it can give us some stability and safety guarantee based on the models. But the bad thing is that we really need a good model. And finally, good model is not trivial. And then we look at another regime, which is model-free reinforcement learning, where we don't really use any models, but just train the robot through trained errors in simulations and approximate optimal controllers. And then the problem becomes how to deploy such a kind of a controller trained in simulation to the real world hardware. And we have a line of research to tackle these problems. But after this tackled, we show that, hey, it's kind of, can work quite well in the hardware to enable a robot to perform agile and robust maneuvers. But it comes with cost that is, since we are using deep neural nets, everything is black box. We have no longer able to provide any guarantees. So then the question becomes, how can we bridge these two methods? Then we find that, we don't need to worry too much, because if for a robot controlled by its well-trained IO policy, we find that the closed-loop system will behave linear as a linear systems. We actually unveil a hidden linear model of a robot controlled by its well-trained IO policies. And this model can be actually embedded in the high-level model-based method. So this is like the mainstream of my research. And we also extend both model-based and the model-free method in enable the black robots to perform, advanced, intelligence in terms of, how to interact with objects and how to interact with other agents to make it multi-agent problems. Okay, so the structured motion intelligence will be the first part, and then followed by in the talk of the day, which will be followed by learned selective intelligence by reinforcement learning, and then I will briefly go through the object intelligence and the agent interactions, and then finally I will bridge the these two methods, the model-based and the model-free, by introducing the linearities findings we discovered. Okay. So then the first part, how to the structured motion intelligence. So usually, it's more like since we have a model, so then we have a structures, to actually explain everything. And usually in this kind of a method, there's no kind of go-to models we used for the robots. But the rule of thumb is that we need a collections of different models, and it will be embedded in different controllers and organized it in a hierarchical way. So basically, when it's getting very, the rule of thumb is that, if we're getting closer to the robot, we need to decrease the model complexity and the prediction horizon in exchange to increase the control frequencies. For example, for the Cassie robot, we really need our control torque, the very last control input torque, a control input, which is a motor torque, to update at 2 kHz. Then we don't, but then in this case, we don't really want our model to be that complex in order to be able to solve in that 2 kHz. So let's give us examples that is we use by robot Cassie to navigate in unknown environments. So in this kind of autonomy kind of research, we first develop reduced order models for Cassie. We just simplify the robot working dynamics and use kind of this sleep model to capture the robot working dynamics. So we just only consider about center of mass and foot placement. And then since it's simple enough, so we can actually run the optimization online and they actually do a very large prediction horizons. And then we can also decrease the prediction horizon in exchange to like higher control frequency to make this kind of controller to be more reactive to such as dynamic obstacles. But these only reduce all the state models, and they only consider about reduce all the states. So, but for control robot, we need all the details, especially when the joint command. Then we actually have a trajectory tracking controller to translate this reduced order model to the full order dynamics of the robot. And these controllers have no prediction horizons, but this is able to update at 2K hertz. And this kind of controller is actually is built on a pre-optimized trajectory libraries, based on the robot full order models. It's actually pre-computed and pre-optimized and online. And we actually create a lot of these kind of trajectories. And online, we just select the, appropriate trajectory for the robot to track based on the reducible model states from the high-level controllers. So anyway, so then we actually, adding the robot visions and all the mapping localizations. Then we enable the biped robot Cassie to, to be one of the first to autonomous navigate in a high constraint environments where there's a, the high constraint, like the arch in front of it. The robot may travel underneath this kind of high constraint space and then recover to a normal height afterwards while avoiding obstacle nearby. While changing all of these commands, robot won't lose its balance on the fly. It's actually one of the first time the robot can do so. And I want to briefly highlight where I inspired, which paper I inspired to make this work happen. This is like a paper from Professor Peter Beals, like 9 years ago, where they have trajectory algorithms to make a humanoid robot to go through this kind of high constraint door, the objective door. And then this only happened offline. So after 9 years effort, we make this happen from simulation happening offline to reality, which can be run offline. And this is actually one of on the list of the most studied articles of Agile in the last 3 years. So we show that model-based method, can do quite cool things, and we also extend to different kind of directions. But the drawback is quite, as we mentioned, we have to have separate for lots of drawbacks. One of the first is that, we really need extensive parameter tuning on the hardware. For Cassie, for our Cassie, for examples, we really need to tune our parameters, the control parameters, from time to time. And if we deploy the same controllers from our Cassie to another Cassie robot for example, at Michigan, we need to do this again. And if we add additional load, we need to do this again. I think all of this tuning effort actually is due to the modeling errors we encountered. We have no way to model all the details of the hardware. And another drawback is that for different robots, we really need different models. For Cassie, we build up entire pipeline using model-based method. But if we go to the digit, which is a humanoid robot in the lab, we need to develop entire thing again. And what about quadruped robot, and what about all kind of different kind of quadruped robots we have? So can we actually make our control don't actually rely too much on the models to make it more scalable method? So then it comes with our second part, which is the learned athletic intelligence, to enable robot to learn kind of mobilities by interacting with the real world. Oh, sorry, with the environment, not the real world. So then in this kind of part, we take the challenge that to say how can we actually obtain a general control solutions to have a same framework to enable the robot to do all different kind of locomotion skills, from running, from walking and jumping. And this work, we just drew all the control problem to the robot itself. We let robot learn to perform all of these kind of skills through trial and errors in simulations by reinforcement learning, and then deploy on hardware. So let's see how it happened. So we first developed our reinforcement learning-based controllers, which is now represented by deep neural nets. The controller, the policy is now, we call controller now as a policy. The policy now outputs the design motor positions as our actions. And this utilized in a joint level PD controller to generate the motor talks at 2K hertz. The policies updates at quite at the lower frequency, which is 30 hertz. So yeah, several inputs. The first input is command. So let's take jumping as examples. So we want the robot to jump to a target after it lands. So we provide the jump landing target as a command for the policy. We also provide a reference motions to tell the robot what kind of motion it should perform. So in the jumping case, we only provide a single jumping reference motions. And this actually for animation is not optimized by dynamics in any way, just handcrafted by human animators. And then we provide a feedback to the policy. The feedback includes a short 4-time step robot input and output history. So now I define what is input and what is output. The input of the robot are the previous policy outputs, which is the policy actions, which is the desired motor positions. The outputs of the robot are observed robot states, which include all the joint positions, joint states, and reading from IMUs and the linear velocities. And then we also keep track of a long I/O history that lasts about 2 seconds, and will be first encoded by a 1D convolution neural net, and then concatenate with other input to the base MLP policies. So in these architectures, we want to highlight the importance of the use of both long and short robot I/O histories. And we will show why. But after this policy is trained, we really want that after this done in trained, we want this policy directly deploy on the hardwares, and then we just give the different commands. The robot can just jump to different commands, give different location as we specified without any tunings. So this kind of very challenging to obtain and realized. So, but before moving on, let's explain why do we need a long I/O histories. That is, if you revisit our dynamics equations, is actually inspired by the adaptive controls in the traditional control method. So if we revisit this kind of dynamics equations, we can collect the robot outputs, which are the robot states, and also the robot inputs, which are the desired motor positions, will be actually related to the motor torques. We can actually collect this input output, and then we can reorganize these equations, and then if we can keep track of a sequence of these input-output histories, then we can actually actively fit in the model parameters of the dynamics models of the robots, and then we can actually adapt our controllers. Okay, so in order to obtain to train such a neural network, we actually.
There's a question.
Yeah.
May I interrupt you, Professor?
Yeah.
So fine. Why 66 steps? Is that where the durability condition tells you to stop, or why 66?
It's empirical results. 66 because our control process is up at 33 hertz. So 66 represent about 2 seconds exactly. And first of all, why do we come up with this kind of number? Is because for the jumping experiments, for a jump, usually the robot will take about 1.6 seconds. So we just have 2 seconds to basically cover the entire jumping time span. And then we go back and then to play around these numbers, what kind of a time step sequence will be optimal for for these kind of real-time controllers. And we find that if we keep increasing the time step, we remember that actually the controller, the learning performance will actually saturate it and even go down because we have more redundant information to put for the robots. So we find that around 2 and 3 seconds is kind of optimal for the kind of locomotion skills. And we actually put in the papers for these kind of ablation studies. Okay, sounds good. And then let's move on. And then, in order to realize this kind of controllers, it's a very challenging training tasks. So then we actually develop a multi-stage trainings, which is namely the curriculums trainings. So first we train the policy in the robot in simulations. And at the first stage, we just focus on mimic the reference motion, jumping in place reference motions. And then in this stage, the motion tracking reward is actually dominating in the entire reward. And then after the robot is mastered this kind of a jumping in place skill, then we start to randomize the tasks. The task is actually parameterized by the command. So basically, we tell the robot to jump to a random target after it lands. So in this stage, we encourage the robot to deviate from this nominal reference mode, jumping in place reference motion, but highlight more on the task completion terms, which is to land at a target. So then the robot start gradually develop a skill to jump to different locations. So clearly you can see this kind of jumping motion is actually deviate a lot from the this original jumping in place motions. So after this skill is mastered, so then we start to randomize all the dynamics. So we randomize all the possible dynamics we can simulate in simulations, such as link inertia, mass, center of mass, including the spring stiffness of cases, and also the PD gains of the motors and adding simulated noise, and a lot of this work. And then we deploy the policies in the hardware without any tunings. So still, this kind of pipeline is quite challenges because if you really want this to happen, we need our policy to have two very nice properties. One is adaptivity. The policy should be able to adapt to the dynamics on the hardwares. So the answer is, if we want to do so, we need to provide a long robot I/O history because we have a sequence of these, so we can actually fit in the model parameters. But once we have these long I/O histories, and it was inevitably recorded by a long, temporal encoders, and the bottleneck, the latent basically will be actually a mixture of the information of both, happened a while ago and very recent. But for real-time control of lag robots, very recent feedback is more important. So we need to have a short I/O history to just bypass this kind of a temporal encoder directly provided in the base policy, and to have explicit recent feedback of the robot states. So we find that this kind of a dual history approach benefit a lot to have a better training performance and have adaptivity in the real world hardware. Second is robustness. We want the policy to be, or the robot to be robust to unexpected errors, while derivative of normal trajectory should be correct itself back. And such robustness is not that trivial to obtain, not that simply by dynamic randomizations. And we found that beyond, besides the dynamic randomizations, we need the task randomizations can help a lot to further improve the robustness of the policies. So then how to structure it, how to have more, practical implementation to implement this kind of the two design choices I recommend to harness to adapt two nice properties. The answer in our papers, we have very nice survey and studies, very detailed ablation, very detailed benchmark and real world result to try to convince you that this kind of design choice you probably can refer to. So then let's show the results. We then we developed this pipeline to enable a robot to perform agile running maneuver in the real world. So now the robot is able to directly transit from the standing to a fast running skate, and then do a very sharp turns, like 90 degrees within 5 running steps. So this kind of control problem is quite challenging because everything is coupled. So robot, and also and then we also enable the robot to, we're actually the first to enable a biped robot to finish one complete 400-meter dash in the real world. So the robot is controlled by a human teleop to control the turning angles, and then the robot need to keep running without falling overs. And the robot can also run over different terrains, and then can transit back to standing. This dash, robot complete this in 2.5 minutes.
Cameraman is horrible.
The cameraman is kosher. Yeah, give a very large credit to kosher. Yeah, all the films are videos are filmed by kosher. Anyway, so this also have we also have a 100-meter dash where the robot run much faster. So the robot finished this dash within 27 seconds, and you can observe a much more significant flight phase and impact on the robot landings. So the robot need to correct itself periodically on this over this kind of time span. So it's very hard control challenges. And then more cool things is that robot can perform rapid transitions from fast running back to stationary standing. So robot is also able to run over varying terrains. So robot doesn't know the incoming terrains, and then it can actually adapt to the change of the terrains. And this kind of a slope, 10-degree slope, is actually the robot can run over to without any information of the terrains. So basically, robot can actually adapt to the change of terrains because of these long I/O histories. And also the perturbations, we also perturb robot laterally while it's running. So robot is able, since robot have been trained with running with different velocities, including the running laterally, so robot is able to actually be compliant to this kind of lateral perturbations and correct itself back to the normal running gait. The same pipeline also enabled jumping. These 4 videos are realized by same controllers, and in fact, in the paper, we realized 19 different jumping tasks by 2 controllers. So these 4 videos have 2 records. One is the first is the standing long jump, 1.4 meter ahead. 1.4 meter ahead. One is the height is table jump, half a meter tall. So everything, and I think right now still this record haven't been broken yet. And everything is like a zero shot. We have no tuning on hardware. And this actually kind of evident to show that the policy is able to be to adapt to the robot hardware, because you actually need to produce quite accurate, translation velocity at this jump as it take off in order to land at a target, because robots have no idea of the positions. So we also provide, SamePilot also enabled, versatile, working skills. So this kind of, okay after you see all the, running and jumping experiments, but I want to highlight that this kind of working controllers is able to have a persistent control performance on the hardware over a very long time span that lasts about 1.5 years. So over this 1.5 years, we consistently test the same controllers on the hardwares. But the hardware actually change over time. It's time varying system because of the wear and tear doing all the experiments, and they really need to tune the parent cycle time for the model-based controllers. But our IO-based controller, these working controllers, does not really need to tune anything. So you can consistently adapt to the changing dynamics on the hardware. It's actually quite cool, and they actually save lots of times. And we also, show lots of kind of a robust test on the robot when the robot jump and we pull the robot on its attack height. Robot is able to correct itself back to the after it lands. So in summary, we propose a general biped locomotion controllers using a control framework using Agile. It can do periodic scales, can do aperiodic scales, can do static scales, can do all transitions from all different scales back to standing. We highlight the proper design choice that can bring the activities. And we want to favor the task randomization. We also recommend the task randomizations in order to improve the robustness. And we also introduce and also demonstrate many novel biped locomotion capacity in the real world. And this paper has been selected as the cover page of Agile and also on the list of most studied papers of Agile in the past 3 years.
Zhongyu, you roughly have 10 minutes.
Okay, then
can't go past time because there's a control seminar after this.
Okay, let me just quickly flash through all of this kind of,
Or choose what you want to present.
Okay, so object intelligence. So then the third part, so we have now able to reliably control a single robot. So how to enable this robot to better interact with objects. So then we start with question that how can we make the legs to use the leg as manipulators while it's in locomotions. So it's quite challenging task because the robot need to be, stay balanced. It also need to manipulate some things during the locomotions. And then, it's coupled by this very complex dynamics. So then we introduce HILMA, which is a general hierarchical locomotion manipulation framework named after Hilma F. Klint, which is who is a Swedish artist, and this is her artwork. So it's actually quite inspiring because it's actually the same as our design philosophy, which is the hierarchical way. We first develop a general low-level IO-based locomotion controllers, and on top of it, we have a task-specific manipulating planner. And the connection of these two layers are parameterized anti-effect trajectories. In our work, we use Bayesian curves. So this kind of very overview ideas what is happening. We first develop a general controllers by IO, and we first let the robot to track a randomized Bayesian curve parameterized by the control Bayesian control points. So we basically randomize everything, and the robot have a quite general, anti-effective tracking controllers. And then when it's common task, such as kicking a soccer ball, then we have a high-level task-specific anti-effector to take into the object informations, as well as robot feedback to specify and to select and replan the Bayesian curve online. So in this way, we enable robot to perform, the precise shooting skills. So in this kind of a demo, we show that if robot can actually shoot a soft soccer ball, but if it directly deploy from simulation to the real world without any tunings, because of the soft ball, there's a very large gap, and all the ball, miss the target. And then this method allow us to just fine tune the planners online using the real world data. So this is actually much more easier to learn by the real world data. So after, when 100 shots in the real world, the robot is now able to precisely shoot the softball to a random target. So we also studied how to compose different kind of dynamic skills. So this framework allows us to add different locomotion skills at low levels. So this is a goalkeeping task where when the ball coming in, if the ball is near to the robot may just use a side step to intercept the ball, and if the ball fly into the goal, robot may use jumping skill to to save the ball. So basically different, and everything happening online, and we actually develop 3 different kind of locomotion controllers, and we have one high level planner to specify which skill to use and what kind of command to use. So this kind of experiment, this kind of interception happens at half a second, and the robot can quickly respond to this kind of fast coming ball and intercept it. So we also extend this to have a residual settings where we actually, and then we enable the robot to perform locomotion tasks while the robot have a sustained mobility, such as just walking around. Or previously, just one time, or robot do just one-time jump, or robot just standing. But in this work, we extend this kind of a framework to make the robot to manipulate something while in locomotions, like sustained locomotions, such as dribbling, precisely navigating goal, and also step over stones, avoiding hitting the stones, directly learning from the vision robot depth visions. So now the high level planner is actually depth vision based. So this also enable us to replace this high level planner from reinforcement learning by imitation learning modules. In this work, we enable robot to learn from the human demonstrations, and the planning directly input the RGBD information in the real world and learn this kind of non-prehensive local manipulation tasks.
What about your dishwasher? I think pizzas in my dishwasher, it's done this correctly.
I said, to be honest, it's kind of limited for leg robots, only have legs, there's no grippers, so can only perform non-prehensive tasks. So anyway, let's summarize. So we've starting from precise manipulation to dynamic skill compositions to all this framework also, here my framework also allows to extend to sustainable mobilities, and also to have a zero-shot planner, vision-based planner, learning from real-world planner, and also learning from demonstration planner, and also extend it to LM planner. So leg robot can do lots of things other than leg locomotions. So also extend, learning-based method, and also model-based method to make it, run to make it, multi-agent settings. So now we have studied the single agent. Single agent can also interact with objects. Now, what about multiple agents?
Now you have 5 minutes.
Okay, so okay, so yeah, so we first started with using a human-robot interaction setup. We let a coach pair robot to guide a blindfolded person. So this is actually one of the first robotic guide dog. It's actually become kind of hit at the community at that time. And in this research, we studied how using this robot to guide a blindfolded person via a leash, and the leash can be either side and top. So you can see when this kind of systems, robot leading human system enter this kind of narrow space, the robot may autonomously adapt the select and the taut mode to find a better configurations to lead this kind of this person to lead through this kind of narrow space and safely. And this person, this person is now scary. Yeah, he's now is my favorite student, undergrad student. Now he's at Caltech doing his PhD. Okay, so then we actually extend to multiple agent to use this kind of cables, select and taut, to collaboratively tow a heavy load. So we show that one agent is okay, but it's not enough. The load is very heavy, and they're quite limited. So you can see when it's gone with a heavy load, the robot may not be able to tow it. So then we have a team of coach pair robots to collaboratively to tow this kind of heavy load through narrow and coordinate each other position to travel through kind of narrow space. So in this experiments, the robot is able to intelligently using the switch of the select and taut mode of the cables to fit into the kind of small gap and then expand expand the cables afterwards, after it's kind of passing through this narrow space. The method also is able to scalable to different robots, up to 12 robots, but this is only simulation animations, so it's not happening in real time because this is actually parameterized. It's usually actually using centralized MPC. It's not that actually scalable for different robots. So we are only able to make this online for 3 robots in the real world. So then we actually extend this method to actually have an actual truly decentralized setup for this kind of a setup. So now these 4 videos are realized by same controllers, and each single robot in the videos are using the same controllers as well. So this actually realized by the decentralized multi-agent reinforcement learning. So you can see that, yeah, so you can see that, the system is quite scalable. Now we are able to realize four agent team in the real world. So you can see for the heavy load, we have the main contributors are basically 3 robots, and the 1 robot, 4th robot, is actually doing some help with after this entire team passed through this kind of a space, the 4th robot start to catch up, to tune the box configuration. But if it's a lightweighted box, the main contributor will only just 2 robots. So everything, all the team formulation actually automatically develop and adapt in the real time. And it's decentralized. There's no kind of formulation planning for these kind of teams. We can also add load while the entire team is like progressing to the goal. And you can see after load is adding, the first robot will actually catch up and to contribute to the total in the load. I think the coolest things is to this kind of method enable us to actually add or remove an agent on the fly. So because of actually decentralized, so we can actually quickly remove 1 agent. So you can see that after it's removed, the first agent will actually catch up with the removed robot rules and still contribute, and using 4 robot team to contribute to the the towering tasks. Okay, safety. So I think
So there's only 1 minute.
1 minute.
So you have time for questions.
Okay. So yeah, I've seen all of the kind of cool things, object intelligence, agent intelligence. Now what about safety? We really need to have some guarantees, right? So in this work, I think it's my most significant research of my PhD, that we actually discovered the hidden linear models of these kind of things. So let's just quickly go through this. I think I've been talking about this for many times. So for R-based controllers, this is a recap. It's a black box with an input as a desired working velocity and working height. Output will be the actual working velocity and the working height. The question now becomes, can we find an explicit model to have this input to actually model this kind of black box? So it's very important, because if we can do so, this closed loop system will now become a new open loop system with a command as input, robot actual tracking result as output. So then we can actually analyze this stability, and also embed it in high-level model-based controllers. So these are, and then in some safety critical tasks. But it's kind of sounds comparing, right? But it's possible. Think about that. Robot is now a super high-dimensional nonlinear dynamic systems. The controller is a high-dimensional nonlinear neural network. Where combining them together, the closed loop system will be easy to analysis. The actual conclusion is quite surprising, that 4 dimensions, working velocity, in sagittal and in lateral, working height and turning rate can be all approximately linear, and these all 4 dimensions can be decoupled from each other. So we actually evaluate these different other controllers and validate in we also provide conditions. So yeah, I just flash over this kind of method because we just perform system identification through the input-output pairs, and we find that it's all linear, and we also apply some stability analysis, and we also cross-validate these different kind of control policies, and we find that the linearity does not always exist, even we're forced to fit linear models. So if it's well-trained, it will be linear. If not, the nonlinearity is still there. So it's actually provide a metric for the convergence of IO. So yeah, it's also decoupled, and we found it very surprised because for this kind of a mass of dynamics, where it's controlled by well-trained IO policy, the closed system now will become linear and is stable, decoupled at minimum phase. And it's actually resembled the feedback linearization controls we studied in the traditional method. So yeah, so it actually can be embedded into, so then it's actually merge everything we talk in this kind of dissertation into one single simulation. That is, the robot is controlled by its IO policies, wheel chain, and then we find the linear system. And then this linear system embedded into the navigation framework we developed at the very first part. And then it's enable the robot to follow a global path while doing navigation, avoiding obstacles, avoiding high constraint, and safely reach the target. So yeah, so it's become right now this kind give us a more like a bird view of what is happening when we actually keep adding more data into the controls. Then this is actually inspiring that is, we actually find that it's actually a spiral from linear control all the way to model-free IO. We find that's not actually one-way route. For when we arrive at the end of the spectrum of this kind of method, when the controller is purely driven by the data, but as long as well-trained and trained by enough data, the closed system will actually behave linear, and we actually can find hidden linear more structures of this. So the more interesting question is, if we go on in the future, if we keep adding data in control, can we actually better exploit the low-dimensional structures in the learning-based control, and where can this kind of still happen in a larger neural network? So in conclusion, we studied model-based method. You have some pros and cons. We also start, model-free reinforcement learning. You saw give us some agile and robust maneuvers, and these, but have some cost. And also extend these two methods into, object intelligence and agent interactions. And then finally, we bridge these two methods by finding and unveiling the low-dimensional linear models, and they can actually combine the advantages from both sides. So if you don't remember all the details, I think the final takeaway is spiral. How do we understand the data in control? So Easter egg, we recently will release our open source humanoid robot. Everything is open source, 3D printed, accessible, and customizable. We want this to further boost the development of a humanoid industry, not industry, entire community and academia as well. And our research have been, through all of this research, I have 3 papers selected as finalist papers in the 3 consecutive year. It's quite cool. And also, I think my favorite paper, and it's also top of my Google Scholar, is the list as the 12th most cited paper in ICRAT that year, over 1,400 papers. And this actually changed the field of locomotion and how the field to change our people perspective, how IO can bring to the controlling and like robots in the real world. So lots of media coverage, because we have some cool demos, including introduce the first robotic guide dog using IO to control robots, as well as some fun attempts in the robot circus. So it's our lab, group video channel. Every time we have a new paper with the videos, we put the videos on these channels. And this is all the videos, since 2019. And these are all my papers. And very happy that. And also, I also have the most cited videos in the group channel. It's also my most cited video paper. Videos have 130K views now. So in the future, I want to push the boundary of the robot cerebellum to the robot brains.
So you want to skip the future work?
Yeah. So basically these 3 aspects to keep pushing the boundary of these 3 axes: agility, intelligence, and safety. So yeah, we just get started to have to make the robot to play basketball.